From water vapor, as on these chilled copper wires, it grows in. We can start by observing the growth of a crystal under the microscope. We will use common salt, sodium chloride, dissolved in water. First, we place a drop of the solution on a glass slide. Water will evaporate, and the salt will... Here it comes, crystallizing in regular shapes, all with rectangular outlines. The fact that they're nearly square in cross-section, and stay that way as they grow, means that the crystal is accumulating sodium and chlorine atoms about as rapidly on one face as on another. If the crystals could keep on growing, uninhibited by obstructions or lack of solution, they would grow large like this one. As early as 1897, crystallographers suspected that this regularity resulted atoms in the crystal. Then in 1912, this was proved through the use of X-rays which fall on the crystal are cooperatively scattered from the various atoms to give a diffracted beam. A diffracted beam will occur only when the Bragg equation is satisfied. Here, lambda is the wavelength of the incident X-rays, d, the spacing between planes of atoms, and theta, the angle made by the M with the atomic planes. The diffracted beam flashes out when the planes make the angle theta with the X-rays. By measuring this angle, we can determine the spacing between the planes of atoms. X-ray diffraction is the most powerful tool the crystallographer uses for studying crystal structure. The patterns made by the diffracted X-rays are recorded by various types of diffraction cameras. Now, this camera has inside it the sample of sodium chloride, which has been placed in the center, and a strip of photographic film placed around the inside of the camera wall. The X-ray beam is directed onto the sample, and the diffracted X-rays from the various planes of atoms are recorded on the film. Here we're using a powdered sample. Any grain of the powder that happens to be in the right position to satisfy the Bragg equation contributes a diffracted ray. The developed film shows the diffraction pattern. This pattern depends on the arrangement of the atoms. The crystallographer measures the positions and intensity lines on the film, and with the aid of chemistry and some ingenuity, determines the arrangement of the atoms in the crystal. This arrangement is called the crystal structure. It may be complicated and take years to determine, or simple like that of sodium chloride. To illustrate the structure of sodium chloride, we will use a purple one to represent the sodium atom and a larger blue one for the chlorine atom. These spheres are about 50 million times the actual size of the atoms as determined from X-ray diffraction measurements. Although we're using spheres to represent the atoms, we don't really know exactly what shape they are. It's spherical. The sodium and chlorine atoms in the crystal are arranged in a regular array in this manner. During actual growth, these atoms are being packed together in a continuous three-dimensional structure whose front is progressing forward here at about 5/1000th of a millimeter per second. This means that orderly layers of atoms are being added to the crystal at the rate of about 10,000 layers per second. We cannot hope to illustrate this rate with the model. Although the model shows every atom lying quietly, we know that in the real crystal, each atom is vibrating a little around its average position because of thermal motion. A crystal, then, is composed of a regular arrangement of atoms repeated in all directions for millions of atoms. And surprisingly, this is true of most solids. There are very few substances which are non-orderly or amorphous. For example, such materials as brass, polyethylene, and wood. If we examine these by means of X-ray diffraction, we find patterns which indicate that their atoms are arranged in an orderly manner, some of them more orderly than others, as indicated by the varying sharpness of the patterns. We can see the crystals in this brass wing nut by looking at it with a metallographic microscope. The surface we're going to examine has been prepared by polishing and etching it with acid. The wing nut is composed of many crystals, a polycrystalline body. The contrast in color is due to the acid acting differently on the differently oriented crystals. Each crystal is grown until it interfered with its neighbors to form an irregular boundary. On an atomic scale, a grain boundary might look like this. The regular array of atoms in each crystal fits poorly against that of its neighbor. In some of the crystals, we see straight lines which are not crystal boundaries, but twin boundaries within this single crystal grain. A twin, or a twinned crystal, is formed when two adjoining individuals share a plane of atoms that fits right into the structure of both, forming a straight twin boundary. This special relationship is so intimate that crystallographers usually think of it as a single crystal with a twinning plane rather than two separate crystals. A crystal may be thought of as made up of identical blocks, each related to its neighbor by straight translation. Such a block is the repeat unit for the pattern and is called the unit cell. We can choose it anywhere as long as we can build up the crystal with it by translation. For sodium chloride, this could be the unit cell, with chlorine atoms at the corners and face centers of the cube. Or this, with sodium atoms at the corners and face centers of the cube. Either would serve as the unit cell of this face-centered cubic crystal. Now let's examine the symmetry of arrangement of atoms around a vertical axis through the center of the cube. If we rotate the crystal around this axis through 360 degrees, we will find ourselves looking at exactly the same arrangement of atoms 4 times in the complete revolution. We will mark one face to keep track of where we are. 1, 2, 3, 4, and we're back where we started. This is an axis of 4-fold symmetry of the crystal, and therefore an axis of 4-fold symmetry of all its properties, because they depend on the arrangement of the atoms. Consider, for example, the property of cleavage. Cleavage is the tendency of a crystal to come apart between adjacent planes of atoms when struck. If we take this large sodium chloride crystal, place a blade on it at any position on the face, so long as we choose the right direction, and strike the back of the blade sharply, we can cleave the crystal. Now, if this is where the crystal came apart, then because of the 4-fold symmetry axis, there should be another cleavage here at 90 degrees to the first. The blade is now at 90 degrees to the first cleavage plane. And there is the other cleavage. Suppose we try to cleave it in any other direction, not at right angles to the first cleavage plane. The crystal simply shatters. This cubic structure has 2 other 4-fold axes of symmetry. Here and here. Though some cubic crystals do not have fourfold axes of symmetry, all cubic crystals have axes of threefold symmetry. Such an axis goes through opposite corners of the cell, like this. If we turn the model so that that axis is vertical, we can check the threefold symmetry. Call the marked face 1, 2, 3, and we're back where we started. We can choose an axis through these other opposite corners, and again we have an axis of threefold symmetry. And another through here. And another here, 4 of them altogether. Some crystals also have planes of symmetry. We can illustrate the planes of symmetry in this cubic structure by cutting the cell in half, first along the diagonal. Now, if we bring a mirror up to its cut face, the cell appears to be complete again. This is because the two halves of the cell are mirror images of each other. The plane between them is called a mirror plane of symmetry, or simply a plane of symmetry. Similarly, this half and its mirror image complete the structure. And there's therefore another plane of symmetry through here. This cubic structure has 9 such symmetry planes. Every property of this crystal must obey all of these symmetry planes, and also all of the axes of symmetry, because they describe the symmetry of arrangement of the atoms in the crystal. For example, the property of elasticity. Consider the elastic strain resulting when you apply a stress along the direction of nearest neighbor atoms, and compare it with the elastic strain when the stress is applied along this direction. You would suspect that they are different. It is, in fact, so. The elastic constants in these two directions are different. And of course, the elastic constant measured in this direction is the same as that measured in this direction because the arrangement of atoms is the same. If we consider the growth rate of the sodium chloride crystal, we realize that it too must be different in different directions. If it were not, the crystal would be spherical. But the exterior appearance of a crystal does not necessarily reveal its true symmetry. This quartz crystal appears to have an axis of 6-fold symmetry, around which the same type of face is repeated 6 times. But is it really 6-fold? Since quartz is a piezoelectric crystal, mechanical deformation will cause it to be electrically charged at the edges between the faces. We can check the symmetry by the use of this property. If we press the edge of the crystal on the contact of an electrometer, we can determine whether the charge is positive or negative. The electrometer is discharged. The first edge is negative. Rotating around the axis in question to the next edge, positive. Another 60 degrees around, negative. 60 degrees around again, positive. Now negative. And finally positive. Alternately, negative and positive. Now we record this on a diagram of a cross-section of the 6-sided crystal. Our axis of rotation is perpendicular to the diagram. The positively charged corners occur 3 times around the axis, and so do the negative corners. Therefore, we have an axis of threefold symmetry according to this test. Well, which is right? Sixfold or threefold? Since the piezoelectric charge in these three directions is positive, and in these three directions is negative, there must be a corresponding difference in the structure in those directions. That is, the arrangement of the atoms must have threefold symmetry. The piezoelectric effect is just more sensitive to the difference than the growth of the crystal is. We can check the crystal's true symmetry in still another way, by etching the surface. This section has been cut from a large quartz crystal perpendicular to its major axis. It has been polished and etched for about an hour with hydrofluoric acid. The surface is pitted, and the edges of each pit form a triangle, revealing again the threefold symmetry. In many cases, the way in which acid attacks a crystal is a sensitive test of its symmetry. We can see this symmetry in a model which shows part of the structure of quartz with the atoms spread apart. Each black sphere, which represents a silicon atom, is surrounded by 4 red spheres, which represent oxygen atoms, and these groups are connected by their corners in spiral array. Looking down the axis of such a spiral, we can see the threefold symmetry of the atomic arrangement to which the etch pits and the piezoelectric properties are sensitive. In order to study the piezoelectric effect in relation to structure, we had to work with a single crystal. What happens if we use a polycrystalline body, like this sandstone, which is made up of quartz grains? If we test it on the electrometer, we get no indication of a charge. This is because the crystals in it are randomly oriented, and though each grain may acquire a charge, the total effect averages out to nearly 0. A parallel experiment, which we can perform with iron and a strong magnet, demonstrates that the magnetic properties of a single crystal also depend on the crystal's symmetry. We place this disc of iron, cut from a single crystal, between the poles of a magnet. Now, this is difficult to do because the field pulls so strongly on the disc. In iron, the atoms are arranged like this. The unit cell is a cube, usually chosen with atoms at the corners and one in the center, a body-centered cubic structure. Here we have spread the atoms apart to make them easier to see. Each iron atom behaves like a compass needle, a magnetic dipole, and there's a preferred direction of alignment of these dipoles. It is along a 4-fold symmetry axis of the cube, in either direction, along any one of the 3. They're all equivalent crystallographically. Now, the disc has been cut perpendicular to one of the axes of 4-fold symmetry, with the other 2 axes, therefore, lying in the plane of the disc. There are thus 4 directions of preferred orientation of the dipoles in the disc. Between the poles of the magnet, the disc tends to line up with all those oriented magnetic dipoles parallel to the field. If we try to turn the disc, it resists until we turn so far that all the magnetic dipoles switch to the next preferred direction, and the crystal aligns itself in the new position so that the dipoles are again parallel to the field. The earlier arrows show the various directions which the dipoles had before they switched. So there are 4 preferred directions in the disc. Next, we place a disc cut from a piece of polycrystalline iron between the poles of the magnet. Mark a point for reference. As we turn this disc, we find that it can be placed in any direction and it will stay there. This is because the individual crystals in it are randomly oriented. Therefore, it is impossible for any single preferred direction to be maintained throughout the disk. Clearly, to understand the relationship between magnetism and crystal structure, we also need to work with single crystals. Although the models we've been using show a perfect array with every atom in its proper position, we know that real crystals are not quite as perfect as this. Small defects occur here and there in the arrangement of the atoms. In the regular accumulation of atoms, one may be left out, creating a vacancy. If part of a plane is left out, the atoms adjust as well as they can. The part where the misfit is localized is called a dislocation. This is the kind of defect we now believe to be largely responsible for plastic flow in metals. It makes it easier for the atoms to change partners. Sometimes a crystal may include an atom where it doesn't belong. If the atom's small enough, it may go in interstitially. Here, the interstitial atom is carbon in an iron crystal. For the atoms of the crystal, its main substitutional atom is phosphorus in a silicon crystal. The substitution of controlled impurity atoms during the growth of the semiconducting crystals, silicon and germanium, determines whether their conductivity is N-type, negative, and about the way in which the arrangement of the atoms affects the properties of solids. Today, in many laboratories, single crystals for research are being grown from fluxes, from water solutions, and from the melt. From studies of these crystals will come a better understanding between physical properties and